dimension reduction. So Martin, thank you so much for yesterday's excellent presentation. It's all yours.
Okay, thank you so much. All right, I'm gonna go ahead and share my screen. Did not mean to. I opened up my email, unfortunately, to look for an email regarding Slack. Okay, so sorry for flashing my email there for a second. But where we left off was in this cluster.ipynb notebook, and we had a really nice, live coding session. It's relatively small, but I think this is kind of great. It's simple and I think very easy to follow, right? Where we have k-means, we have PCA, and we have pipeline, and we use pipeline to wrap up PCA and k-means into a single object, and then we oh, here we go. Here's something that I needed to do. I should make this be PL instead of model, right? But it works just fine. And then I get the cluster labels, right? So these are our predictions, okay? So in terms of, and then for this plot, I would need one more thing. I would need actually the transform data. This PL object, it has get feature names out method, right? But then when I call it, it's saying it doesn't have from PCA. Okay, so some of this, what I'm trying to say is there are some drawbacks to using pipeline. It may not be able to reproduce everything that we had in the flow. From before, when we did these things separately, we had PCA, so that's dimensionality reduction, and k-means, and that's clustering. We had them separately, right? But here we still have fit transform to get out the data, the PCA transform data, and fit predict to get out the cluster assignments. And I think that's about it. Okay, so we have our cluster labels. We use those cluster labels in this plot. Let me now show that we get the same plot. Okay, so it looks, I mean, the colors are different, but because the numbers, the numbers and the colors, those are arbitrary, doesn't matter. But when I look at these, they look the same. So we're getting the same cluster assignments, but this code is much simpler than what we did before. What we did before, we had to instantiate PCA, use it to transform the data, instantiate k-means, and use it to get the predictions. Okay. Whereas down here, we instantiate pipeline with the PCA and k-means instances, and then we just call fit predict, and there's a lot less there. It may not seem like there's a lot less code because it's roughly the same number of lines because I broke this up into separate lines. But if you compare the two, this is a lot simpler. I'd say a big improvement. Okay.
So Professor, can I ask another question?
Sure. Yeah.
With those two lines, the PCA, PCA end component equals 2, and the k-means, I'm getting an error that the tuple object is not callable.
Not callable. Yeah. So what I think, it has to do something with the structure of the code. So it has to be set up like this. When you have pipeline, usually when you get an error, something that's useful is to just separate out the code that we want to run in its own cell. And then so the tuple is this thing. So it's wrapped in parentheses, right? And then what I have here is a list of tuples. So the square brackets that surrounds a list of tuples, and I have two tuples here, right? Maybe what we can do is if you could maybe share your screen.
It actually just worked. I think I didn't have commas in the tuple.
Okay,
So,
that's what
yeah.
it is. Okay, okay.
That was already helpful. Thank you.
Okay, okay, good. So really quick, maybe some basic Python concepts that just in case anyone is interested in this, it could be useful, right? So the most basic tuple that we can have is going to be any number or anything and then a comma, right? And then when it's alone by itself, we actually just need the comma, right? So 2 comma gives me a tuple. It's a tuple with only one element, right? Here we need to wrap it in parentheses, and then have the tuples also be separated by a comma, right? And the way that I have it here is I've got a trailing comma. This last comma we don't actually need. But the reason that I have it there, it actually has a useful purpose, is because here I wouldn't want to change the order, right? PCA has to come before k-means in this example. But in another situation, if I did want to change the order, I can do it easily. And these lines are then interchangeable. That's why I always add this trailing comma at the end, right? But what we have here essentially is we've got 2 tuples, right? So this is 1, right, surrounded by parentheses, and this is another. Yeah. So we got another chat message. Okay, so there's a link to the Slack. I'm gonna open that up. Let me take this to a separate window. All right. Okay, this is good. And then I should be able to now join the Slack, and I can share. Good. Okay. I should be able to now share things with everyone via Slack, which I think is going to be very useful. All right, and now, okay, so I'm in. And module 3, look at that, there's a channel and I'm in there. Oh, wow, that's great. Okay, so that's what I'll, let me just put, hi everyone. All right, so I'm in the Slack, which is great. And I'm going to be able to share code that way, okay? All right, but let's move on. So this was pipeline doing PCA, doing k-means, right? Actually, before we move on, let's do one quick thing where I'm going to ask another question. You know, I like to ask questions, right? So if you were here yesterday for the first part of this module, what's the reason why am I using or why did I want to use PCA here, right? I talked about how this plot, right, didn't make much sense to me, right? It was counterintuitive, right? This one here, right, was counterintuitive. But this one, when I look at it, it makes sense to me, right? So what advantage does PCA give me, at least in terms of plotting, just in terms of visualization, right? And you can answer in the chat or just unmute and let me know what you're thinking. Okay, so it's dimensionality reduction, right? And so what is, reducing the dimensions, why is that helpful specifically in terms of plotting? Right. Okay. And here, while we're waiting for a response, I'm gonna put in something here. So, okay, so here we have fewer outliers, irrelevant data, cleaner plot, perhaps. Okay, great, lots of great ideas. So in terms of fewer outliers, there will still be these outlier values. They still will be there, except, they will. There is some I think control in there for the outliers. And what I'm thinking about is if there's let's say one value that just happens to be for one variable super high, that's going to matter less than really, kind of how connected all of the variables are, right? So we're kind of collapsing several variables together. The variables we're collapsing are going to be correlated to some degree, or else they won't have any impact on each other. And I think there is something to be said that the outliers, there's going to be maybe like a mitigation of outliers, right? And then irrelevant data, that's actually a brilliant thought, because you can have irrelevant variables, and your PCA will make it so that those really won't matter. I could add many columns of noise, and the PCA will say, okay, those are not correlated with any of these others that really explain variance in the data set. And those won't matter. We probably won't see those correlated with things that matter for the data set, for explaining variance in the data set. And so they are not likely to be included at all or have an impact on those first principal components. Principal components are these variables coming together after we do dimensionality reduction, right? So we have a lot of variables and we're collapsing them down into one. So irrelevant data, I think, is absolutely right. I think all of these are right, actually, everything you've suggested. And then cleaner plot. So it is regarding the plot, right? And here I have my principal components, right? So I'm going to say the X label is PC1, and then the Y label is PC2, right? So here the major difference between these is that I'm looking at principal components, right? And not any pair of variables, right? So there are going to be, these principal components, they're made up of something, absolutely. And they are composed of variables that I passed into to PCA, right? And here I'm collapsing from 4 dimensions down to 2. Collapsing down to 2 dimensions is common, so then you can do this PCA plot. And what it allows us to do is to distinguish between points well. And then if I use those principal components also for clustering, then I get a plot that includes really information from all of the variables, but it's 2-dimensional, and it makes sense. So I can see here that the clustering is logical. You know, I see all the green points are together, right? And I can see all the blue points are together. Whereas what I showed previously, this other plot here, right? Because I'm plotting 2 of the 4 variables, and I'm using all 4 variables, right? For k-means, right? There's kind of a disconnect. I'm using PCA to plot, but I'm not using it for clustering. And then here there are 2 dimensions that I can't see. And so for me, it looks like the orange and the green points are mixing. And I'm left wondering what's up with my clustering algorithm, that it's not doing this. It doesn't look right. It doesn't look clean. Okay. And so this is actually a good place, I think, to use PCA, at least, you know, for visualization and plotting. If later on we decide, oh, actually, we want to use these 4 features, these 4 columns separately, we don't want to put them together into principal components, right? Then that's fine, but at least for visualization, this is super useful, right? And for data exploration, it'll have a you know, I think a really good result, right? Okay, so I showed how we've got this pipeline object, right? And it's going to have things provided from each of the things that it contains. So fit predict is coming from k-means, fit transform is coming from PCA. PCA is treated like a transformer, and fit predict is an estimator, right? So k-means is an estimator. It has a predict method. PCA is treated as a transformer. It has a transformer, right? So in scikit-learn, there's this distinction between these 2 types of classes. Okay? And then when we have PCA on its own, right? So this is from before. So here I instantiated PCA and then I fit it. So I should have PCA fitted there. There I'm going to get some potentially useful information, right? So what's the number of components? I had 2 components, right? The explain variance, right? So of the 2 principal components, how much variance did they explain? And then what's the ratio, right? So the first principal component, it explains 92% of the variance. Okay, so it's very, very powerful, right? The second principal component only explains about 5% of the variance. And really, how would it look if we were just using this first principal component? Yeah, we wouldn't have any information in this vertical direction. Imagine if everything was just on a line, okay, on a number line. What would we have to do then? We would have to draw our clustering algorithm, at least, would have to come up with some kind of a rule. We can see here that in 2 dimensions, there's the decision boundary. Let's maybe use a vanishing pen. 1 second. Vanishing pen is nice. So the decision boundary looks like this. Okay. Between cluster 2 and cluster 0. Okay, it's between green and blue. Okay, so that's the decision boundary here in 2-dimensional space. In 1-dimensional space, right, we would have to pick something that's essentially a vertical line, right? We would have to do something like this, probably. And that wouldn't be as good, right? So here, the second principal component is definitely helping. But a third principal component probably won't be that helpful. There's only if you think in terms of variance that's left to be explained, there's only, you know, if we kind of combine these together, really what it's going to be is going to be like 2% variance that isn't explained by these principal components. And that third principal component, it would be, we'd have to show it, we'd have to use a three-dimensional plot. Okay. And three-dimensional plots are, you know, sometimes difficult to create. Certainly in Matplotlib, which is what we're using here, that's a Python library. 3D plots are a pain, actually. And they're harder to read than two-dimensional plots, okay? But an important observation here is that the variance explained by each of these principal components, you know, for the first principal component always explains the most variance. Then the second one is second place, and third is third place, and so on. That's how the algorithm works, is we take the things that are, you know, they move in the same direction, but are best at separating out the data that kind of give us the best spread, right? And we can see that here actually in the in these numbers, right? So, you know, if you look along this axis, it goes from -3 to 4, and there's a huge separation between this cluster 1, which is orange, and the others. Okay. If we were looking only at principal component 2, we really wouldn't be able to differentiate between the clusters at all. Okay, I think it is helpful here, like I mentioned, like we can draw a decision boundary that isn't necessarily, you know, a straight line with 2 dimensions. That's great. We can do a curve. But here, if you can just imagine, if this were the number line, everything would be overlapping. Okay. So how would I describe the orange cluster, your cluster 1? I would say it has very low values for principal component 1. Okay. The other two, how would I describe them? I would say, okay, well, green has low values. Well, it has you know, values, let's say between -1 and let's say 1.5 for principal component 1. Okay. And then in general, lower values for principal component 2 than cluster 0, right? So cluster 0 is high in principal component 1, and then also higher in principal component 2 than cluster 2, right? So I can come up with, if I was just using principal component 1, I could do a pretty good job of separating them, right? So basically the green is going to be to the left of this blue line that I drew. And the blue cluster is to the right of the blue. Okay, that I could use that. I could use just principal component 1, and it would work fairly well. Right? If I was using principal component 2, how would I describe it? Where could I draw a horizontal line that would help me distinguish between the clusters? Probably, you know, I wouldn't really be able to do it well. I could draw a line maybe here and get some of the green points, but it would be mixed with orange. And then above that line, I would have a mix of orange, green, and blue, right? So certainly principal component 1 is the most useful. That's a common thing, right? We get the best spread of the data points from the principal component, from the first principle. Okay. All right, so that's an important concept for dimensionality reduction, certainly for PCA. And you can use many different kinds of algorithms for dimensionality reduction. But the way that you plot it, the way that you think about it is very similar. You'll still have your two principal components that you're going to be plotting. Right? Maybe, and then one thing that I think I noticed is that this pipeline object, it doesn't have I think, explained variance ratio. And so that's a little bit of a, I think, a little bit of a limitation, right? Maybe there is some way that I can access PCA from pipeline, but it doesn't seem, I can't think of a way off the top of my head. So if you do need these things separately, then pipeline probably isn't the right choice. But if you don't need each of the steps in the pipeline separately, then this is really convenient to combine them together. Right? And this is just for a two-step pipeline. If we had more steps, it would the gains would be even greater. Yeah. And by the way that I'm looking at what an object has is I type in the object name, I press dot, and then I press tab. So tab gives me some suggestions, and then I can look at what these are, right? So here's a dictionary, name steps, PCA. I get out PCA and components. And then if I take explain variance ratio, great. Okay, so that's how I would do it. Okay, so it seems like from the pipeline I can access it, right? So I was thinking somehow get to the steps, right? So named steps, I can use it as a dictionary, and then PL steps, right? I would pull out the first one, the first step, and then get this explain variance. So tuple has no attribute. Okay, so I'd have to actually get, take the first tuple, then get the second item, the one indexed by 1. And that's how I would do it. Okay. To get out this information. So how much of the variance in the data is explained by each principal component? And I think that's probably the most useful piece for now. There is one more thing that I would want to do with this. So say, you can also see how many features did we start with. We started with 4 features, but now we have how many? We have n components, right? We have 2 components, right? There are a number of methods here, like get precision. That's really interesting. That we might want to use, get params. These are the things that were passed, or the settings for it, right? Okay. And then those things are also available from the pipeline, but then we have to access it either through steps or named steps, right? So the pipeline object, we can access the k-means, right? Sorry about that. We can access k-means, we can access PCA, we can access any of the steps there. Okay. So let me show. All right. So here, this is the PCA. Right. I can also access k-means, and then there's probably going to be an n_clusters. Yep. So here for the k-means, I put 3 clusters. Right? And actually, there's going to be, at least for the training data, there's going to be a thing called labels, right? So in the code that I have, where I created those cluster labels, I could have done it differently, right? So instead of you're doing fit predict on the data, because it's the original data, I could have just used this labels, right? So let me show you what I mean. So I'm going to put this in here, right? And then pull out the cluster labels. Yeah. So that's really, really nice. Okay, good. All right, I think that's it. Let's get ready to move on. Now, again, I'm going to make a comparison, okay, with classification. Okay. Now, for the previous module, you did classification. And if I say something that's incorrect, you say, oh, we actually didn't do classification, definitely correct me. Okay. I believe you did classification. And for classification, you probably had some way of assessing how well the classification algorithm is working. Okay. Can someone say what's one way you can assess, or what's a metric that you can use to assess the performance of your classification algorithm? Okay. And if I don't hear from someone, I'm going to call on someone. Let's see. So I called on a few people yesterday, and I had mixed results. Okay. Let's try. And I just want to have a conversation. You know, if you can't think of one, that's fine. But let's see, Noah. I hope I'm pronouncing your name right. N-O-W-A-H. And then I'm also going to be looking in the chat. If I get a response in the chat, then I'll stop trying to call people out. Okay. But if you did classification, right, you're going to want to assess how it works, right? Confusion matrix, brilliant. Okay. So confusion matrix is a great way. And then I'm going to show you specificity. Well, let's just look for specificity on Wikipedia. Specificity, sensitivity. There's a great table that they have, right? Lots of equations, but then there's the table here. In this table, the part that's the confusion matrix is this. It's also called a 2x2 table, also called a contingency table. Okay. Oh, sorry. I need to go down a little bit. Needs to be like this. We're so close. Just out a little bit more. Okay, good. So this is the confusion matrix. Okay. So what do we have? We have a predicted condition and then the actual condition, right? So this is predicted, what our algorithm is predicting, and then actual, this is the truth. Okay. And we've got true positives, true negatives, false positives, false negatives. And from this, there are many things that we can calculate to get an idea of how well our model is performing. The simplest one is just overall accuracy. Okay. So from the confusion matrix, actually, Emmanuel, you had the best answer for confusion matrix, because from the confusion matrix, we can calculate accuracy, right? We can calculate positive predictive value, negative predictive value, true positive rate, true negative rate. We can calculate all of them. Basically, what we do is we take, for example, for true positive rate, our true positives over all of the positives. Okay. And we can calculate really all of these metrics just from the confusion matrix. Okay. Now, for clustering, we don't really have that. We can't really do that. Okay. And the reason why is we don't have labels, right? So all of these metrics there that I mentioned for classification. So true positive rate, true negative rate, positive predictive value, negative predictive value. Those are the four that I think are worth mentioning. All of those require some knowledge of what the actual answer is, right? What's the label? For accuracy, you see correct predictions over all predictions, right? So you have to know, how are they correct? Well, the prediction, when the prediction matches the actual, then it's correct. For clustering, we don't know. We don't have the real labels, right? So we have this problem, right? How do you measure success without the true labels? Okay. If we do have the true labels, we can use any of these methods for classification to get the answer. And let me show you an example of that. So let's say we do have the labels, right? So I would have to then see, we have our cluster labels, right? And we have our Y. I believe we have a Y. Yep. And those would, here, I'm not sure if the zeros, ones, why are there 0, 1s, 2s, and 3s? I think something, this is something different, right? So what it's going to be is it's going to be iris, right? I've got here, and then it's going to be target. Okay, that I know is good, right? So I've got my zeros, my 1s, and then my 2s, right? And then what it looks like here is in my cluster labels, I've got cluster 1 is actually encoded as 0 in the target, right? And then cluster 2 is target 1. Okay, so I'd have to make a little bit of a change there. Let me make that change right now. Okay, so I'm going to turn it into a series, and I'm going to use the map method, and then I'm going to use a dictionary. So I've been doing this for a while, so I kind of, when I have to do something, I know exactly what to reach for. There's no shame in Googling these things. You can just say, I need to recode my target variable or something like that, right? How do I do it, right? So the way that this is going to work is I'm going to say 1 becomes 0, 2 becomes 1, and then and then 0 becomes 2. Okay, so I'm turning this into this, basically. Okay, so let's look at that. So I turned it into a series. It just looks different. I could turn it back into a NumPy array, and that's fine. Okay. So let's have this. This is going to be our predictions. Okay, and this is going to be our actual. Maybe I call it actuals. That's fine. Let's just call it actual. Okay. So I have predictions. I have actual. Let's look at predictions one more time. Good. I think this is good. This map, it's very important for me to run this only once. If I do it again, it's gonna cause problems, I think, right? Okay. So now let's go ahead and import something, right? So we're gonna say from sklearn.metrics import accuracy. Okay. Accuracy score. All right. So then I take accuracy score and I drop in my I always forget what the order is. Let's say actual and then predictions. I think it doesn't matter, but yeah, that's right. It's actual and then predictions. Okay. So what's my accuracy here, right? I could say my accuracy of clustering is about 89%, rounding up, right? So that's pretty good. Yeah. I'm looking at how well these match. Okay, the target, the actual species versus the cluster. Okay, so there's a pretty good match. Okay? But this is if I know what the species is. If I don't know what the actual label is, and that's probably the actual use case for clustering, is you don't know what the actual label is, right? Maybe you don't even have a potential label in mind, right? So in that situation, you would use clustering. Whereas otherwise, if you do have the label and you just want to know, I want an algorithm that predicts the species, you would use classification rather than clustering. Okay. And so in a situation where you don't have the actual class labels, right, we can use something else, right? And the two that I'd like to highlight are silhouette coefficient and the elbow method. Okay. The other ones, okay, that we could use for assessing how well our clustering is working, adjusted rand index, mutual information-based scores, homogeneity, completeness, V-measure, they all require some knowledge of the label, of the ground truth, of what is, what are the answers, right? If we don't have the answers, and that's common if when we're doing clustering, we're basically doing the best we can without the answers. We would use silhouette coefficient and then the elbow. Okay. So here I'm importing metrics and then showing, adjusted rand score, right, which is a common one, but I'm going to kind of skip through this. This I'm just kind of providing for completeness to show what things are available if you do have the correct answers. But what I want to focus on here is this elbow method. Okay. And so this elbow method, what we can do is we can get out those inertias. And if you remember in k-means, right, there was this concept of inertia, right? And so this was sum of square distances from a sample to the closest cluster center. So a sample is a data observation and a cluster center is a centroid. If you remember those centroids that we're moving around, right? Okay. So we have these distances of each data point to the cluster center, and we're squaring each of those distances. What does squaring do? Squaring makes it so that positive and negative distances, these are kind of like, the distances won't be negative, but basically squaring makes sure that if there's a negative number in there where positive and negative numbers won't cancel each other out. And then we sum it all up. So we aggregate it into a single number. So inertia gives us a single number that describes a model. Okay, describes a clustering algorithm. Okay. Okay, so the elbow method uses this thing called inertia. All right. Good. And then this thing of, sum of squares shows up in a lot of different places. Okay. But these values here, SSD, that we're seeing on the y-axis, these are these, sum of square distances. Okay. And we've got our elbow plot, and we're going to be looking for where's the inflection point. Okay. And here, the inflection point, really what I see as the elbow, where we start to plateau is 3. But here there's it's kind of a gentle curve, so the inflection point may be a little bit hard to see. Okay, and then For k-means, we fit the k-means. Now the interesting thing is this data set. We're getting, I think, do we have something called data set? So here I have to fix this again. I think it's because yeah, so I'm using iris, and what I need to be using is iris 4D. Okay, so plot the elbow. And here I think it's more clear now, right? You see how I'm doing this in 4 dimensions, and then it starts to plateau certainly at 2, but then I'm still getting some benefit from going from 2 to 3. But then to 4, this is really looking like a flat line. And then 5, 6, 7, 8, that's really, you know, there's not a big difference between, right? So this is a subjective method. And it'll partially also depend on whether you want to have 2 clusters or do you want to have 3 clusters. It's kind of up to you. Maybe someone will say, look, you know, the best one is actually 8. But I say, hey, no, 8 is too much. We have to assign meaning to all of these things. We have to say, what do they mean? And if 8 clusters, I just don't want to deal with that many, right? Let's do 3. I can come up with stories for 3 clusters. I don't want to deal with it, right? So it really depends on the situation, and it's a subjective method. You could programmatically determine what's the inflection point. Yeah, but I think there's not too much value in that, because anyway, you're going to want to look at the plot and make this decision based off of your knowledge of the situation, right? Okay. So there's a little bit of a thing that I want to say here. So this function uses a for loop. But what I always like to say is, you know, maybe what we can do is avoid doing that, right? So what I would want to do is take this iteration logic from our for loop, okay? Take our k-means, okay? Fit it to the data set, right? And then pull out the inertia. Okay? And that's it. Okay, and so we're going to say how many clusters. And so in my example here, I'm going to have to do max clusters equals 10 separately. And then for the data set, I'll do iris 4D. So maybe it's not worth creating a variable. I'm just going to say here 11. Okay. Now let's do inertias. Let's call this inertias. Okay. So I've got a list of inertia values. I'm gonna just maybe put some line breaks in here because I think it's gonna make the code easier to read. Yeah. All right, and then the final line. Okay. So what's going on here, right? So here I've got k-means, and I'm fitting it, and I'm getting the inertia, and then that's it. And essentially, I kind of throw that thing away. That's what's happening here too. But the main difference is that here I'm using a for loop, and here I'm using a list comprehension. So list comprehension in Python is a way of iterating that will give me a list at the end. So list comprehensions create lists, okay? And I would maybe just make a small change that say having 1 cluster is meaningless. So I would start at 2, right? It's not useful maybe here as a point of reference, it's useful to plot that. Okay, so maybe but it would never be the right answer. It wouldn't help us at all. Okay, and then we can be sure that putting everything in one cluster will give us very large distances. And so the sum of square of those distances that's going to be the highest value. So k-means with k equals 1 is going to be the worst ones. Okay, we want the sum of square distances to be as low as we can without having just needless clusters. So we're not really seeing any benefit from going from, let's say, above 4, right? It's really a plateau. We're adding complexity to the model without seeing any benefit. Okay. All right. So that's great. Okay. And we've got now our elbow plot. We can look at this and make a judgment call and say, okay, here the elbow maybe is at 3, maybe the elbow is at 2. Again, it's, a judgment. Yeah. Okay, this plot I think is really the same as before. Here where we've got inertias, right, and we're comparing those to this these ARIs. So that's an adjusted RAND score. And the reason why it's ARI is it's adjusted RAND index. Okay. And if you look, yeah, even the documentation here says RAND index. Okay. So don't worry too much about this RAND index. This is just kind of a comparison, right? So for the most part, these go, there's kind of a linear relationship between them. So when there's a linear relationship between them, I would say they're interchangeable. But in some cases, they're very different, right? So here, if you look, one cluster, having a single cluster, so k equals 1, has a very high sum of square distances, but a very low adjusted randomness. Right? And so this is kind of an outlier. These others kind of fall on the same line. But the here, this one is one that we really wouldn't consider, right? Interestingly enough, if you look at something here, this 3, it's still on the same line, but for the adjusted RAND index, it's essentially, better than the others, right? So adjusted RAND index is interesting. The inertia will continue to go down as we add more clusters. But adjusted RAND index, we have some way of normalizing this to say, okay, is it worth it to add more clusters? And if we look at 3 clearly stands out. It's better than the others. Okay. All right, so the ideal ARI would be 1. Okay, and again, if we look at the documentation, right, okay, so adjusted RAND index is going to be 0 for random labeling, right? If we're really completely just our predictions are random, our cluster assignments are random, versus exactly 1 when you have your cluster labels match the actual labels, right? Okay. And cluster labels, that's a word that's used by scikit-learn, so it's fine to say that. And then scikit-learn also has k-means doing prediction. Okay. And then, so really what clustering here is doing, using the scikit-learn nomenclature, is we're creating labels when we didn't have any labels to start, right? Whereas classification, we're generating labels, but based off of the labels that we started. Okay. All right. Let's move on to silhouette coefficients. Well, actually, maybe before we move on, really quick, If you could let me know in the chat, have you seen a list comprehension, something like this, before, right? So I'm going to gauge your familiarity with Python. If you haven't, that's fine, but this is something that I use all the time in Python. And so if you're not familiar with it, I think it's good for us to talk about it, and I'll maybe try to throw in another list comprehension in later. Okay. All right. So here we've got our silhouette coefficient. There's maybe another thing for different types of clustering, right? So here we've got a hierarchical clustering dendrogram. That could be something that we might want to do in order to kind of understand. It might be helpful to understand our features. It might be helpful to understand our observations as well, right? So that's something that I just thought of right now that we may want to do. Okay. So let's try that, because I think we didn't have that. So for that, I would use SNS heat map. Oh no, sorry, isn't it cluster map? Yep. And then I would do iris 4D, the 4-dimensional one. And then I would say cluster. I think, okay, so let's just do it with the default, right? And I'm gonna get 150 is a lot, right? Okay, but so here, in terms of the rows, what I might want to do is I might want to get out 3. Okay, I might want to get out 3 kind of clusters from hierarchical clustering, and this one up here, right? Comparing this to our plot, right? So the one up here, the one that stands out the most, is going to be cluster 1, this orange one here. Okay. All right. And these down here that are more similar, right? It's kind of harder to pick them out. These ones are going to be cluster 1 and cluster 2. All right. And up here, we're going to have petal length, petal width, sepal length, sepal width, something like that, right? I don't actually know which is which, unless I look down here, right? Let's maybe try to zoom out a little bit. Okay, good. And so here I have to zoom out one more time. Good. And so what do I learn from this, right? Well, which ones are actually the most similar? Wow, surprisingly to me, right? The ones that are the most similar are sepal width and petal length. So that kind of doesn't match my thought process, where that the petal features would be closest together, right? But the two that are most similar are sepal width and petal length. And then petal width is closest to those two. And then sepal length is the furthest from those others, right? Okay. And then this also gives us a pretty good view. So this cluster that stands apart, that one is low in petal width, so has narrow petals, and low in petal length. Yeah. Good. There's another thing that maybe we would want to do, and this we haven't done, is just to simply plot the data instead of using the labels, right, to be the cluster, right, we might want to actually use the species, right? But maybe let's not worry about that for now. But I can tell this cluster here has overall small petals compared to the others. Okay. And then for sepal length looks like it's maybe not as useful for distinguishing things. It seems like petal width and petal length really gives us at least a big distinction between this orange cluster and the others. Yeah. And so if we look at PC1, how would I explain PC1? Well, it seems like really what it is it's being heavily influenced by petal width and petal length, right? And then this orange cluster is low in both, right? Okay. So what would be one way that I can describe PC1? Well, it would be, let's say, petal size. Okay. One way that I can kind of intuitively think about it, and interestingly enough, that's exactly what I was talking about when I was explaining Pca yesterday. Okay, so I think this is useful, and this is super easy to do, and I'm just using Seaborn's cluster map on its own without specifying any kind of arguments. Okay, I'm just passing in the data. That's it. Okay. All right, let's jump back to silhouette coefficient. And here we have some nice code, yeah, to plot silhouette coefficients, right? Now, for these silhouette coefficients, we're plotting them individually for each cluster. And when we look at the equation for calculating a silhouette coefficient, you'll see that essentially that makes sense. Okay, so we have silhouette coefficients for cluster 0, cluster 1. We can also do this for three clusters. Okay, this dotted line, what it is it's going to be here we have X score, right? So score is the silhouette score. That's the average silhouette score across all the samples. Yeah. All right, so we kind of average the values and we have this dashed line, right? All right, so let's talk about this, right? So silhouette score, we've got this B minus A over the whichever is larger, A or B. Okay, so pretty simple calculation, I think, right? But what's B, what's A, right? Okay, and so A is going to be the average distance between a sample and all other data points. So it's the distance between the data point and all the other data points in the same cluster. Okay. All right, and then what's B? B is the average distance between a data point and all the data points in the closest cluster that the data point in question doesn't belong to. Okay, so let's look. Okay, so basically we're talking about within cluster distances and then also distance to the nearest cluster. Okay, so let's pick a point. I'm going to circle a point, and we'll talk about this today. Okay, so here, oh, why did I pick blue? That is not the best color, right? So let's pick orange. Yeah, orange is going to stand out here. So let's pick a point that stands out fairly well. Let's Oh, I'm gonna have to pick a circle. Yeah. So let's pick this point here. That data point. Okay. So my circle looks pretty good. Now I'm going to draw some lines. Okay. So I'm going to get all of the distances between this point and all the points in this cluster. Okay. In the same cluster, the one that it belongs to. And then, please forgive my drawing skills. Right. Clearly, I'm not going to be the world's greatest artist, not in this lifetime, right? And so here you can see I'm kind of drawing out all these distances, and it's actually not looking that bad. Okay, so maybe I'm being too harsh on my drawing skills, right? And I get all of those distances, and then I average them, and that gives me A. Okay, so here this orange, that's A. All right, and I'm going to now pick another color. Let's do brown. Okay, then what I'm going to do is I'm going to get the distance between that point and all the other points in the nearest cluster. So the nearest cluster clearly is green. Okay, so I'm going to get these distances. And these distances, when I average them, that's going to be B. Okay, so of course there are a whole lot more lines that I would need to draw, but I think you get the idea. So I have all these distances, and I'm going to combine all of these orange lines that I didn't finish drawing all of them, right? The average of the lengths of those orange lines, that's going to be A. And then the average of these brown lines, again, I only drew 3. I'm missing 47. I know. Of all of those, the average of the lengths of all of those lines, that would be B. Okay. All right, so I've got my A and I've got my B, and then I just plug those values into the equation. But you see how every point there gets its turn being kind of like the focus, right? So every point gets a silhouette coefficient, right? So silhouette coefficient for a single sample, example, instance, it's following this equation, right? And so max AB, it's whichever is bigger, right? And looking at what we saw, the bigger one is going to be, in this case, B, right? So unless there's a point that just happens to be, there's kind of like mixing of points, and you have, that point, it may switch over, but for most of these points, what it's going to be is it's going to be B minus A over B. Okay, so it's kind of normalized to some degree. Okay, so there's this division. Okay, all right, and okay, so let's look at the results here for these silhouette coefficients. So we can average everything across all the clusters. We get this dashed line. And then each, maybe let's say line here is going to be a sample. And then together, they form this kind of a waterfall. Okay. And then each of these clusters, just, they're more or less the same size. And so I know we have 150 observations. So in each of these clusters, we have around 75. Here, the clusters are not the same size. Okay. And I can see cluster 0 and cluster 2. All of their silhouette values are larger than the okay. All right. And I think here this is the same plot, except it's just the colors are different. The colors are random. It doesn't really matter. But we can use something like this to assess our clustering, right? So let's look at 2. All right, so 2 gives us an average silhouette score of, let's say, 0.48. A 3 gives us an average silhouette score of 0.6 something, right? So it's better, right? In this one, I'm going to change it to be 4. Oh, sorry, I need to run this code. Good, 4, okay. And you see, so the silhouette score is better here. Okay, I've got 4 clusters. Let's go ahead and do 5. Okay, so what happened, right? Here, our silhouette coefficient actually has gone down, and it's less than 0.6. So according to the silhouette coefficient, 4 appears to be the best, right? Okay, let's take a look at this. All right, so it actually looks like it's getting different values here. So that's so interesting. Let's take a look at this. All right, so silhouette score we have from scikit-learn, right? So these distances, in terms of within cluster, we want A to be small, actually. So I think the lowest, so here where it says the silhouette coefficient, the best value is 1, the worst value is -1. Values near 0 indicate overlapping clusters. Okay. But the thing is here, what I see is different than what I saw over there. And I'm a little bit interested. Here I'm doing data set and then the labels. So the question is, why am I getting different scores here versus this? Yeah, so maybe what I want to do is actually take this function and have it return the score, okay? And then I want to do, see, here's another example where I want to use a list comprehension. And I'm going to plot these silhouette diagnostics. I'm going to do I for I in range, let's do 2 through maybe 11. That's what we did before, right? And then these are going to be my scores, right? I'm also going to generate a lot of plots, but that's okay. It'll be interesting, right? So here's 4, here's 5, here's 6, and you can see some of these are really looking bad, right? Where they're looking very jagged. There are a few points in that cluster. The overall silhouette coefficient for that cluster is very small. So what it looks like here is that we've got one useful cluster, which is cluster 0. In those cases, here it's cluster 2. And the other clusters are really not that useful, kind of jagged. And then here, for this last one, where we have 10, it just, it's hard to even make sense of it, right? So we've got some some jagged clusters, and overall the silhouette coefficient is very small. All of these are rather poor, right? So we could look at it this way and say, well, which one looks sensible? 4 has the best overall, and it looks quite sensible, right? We have 4 fairly evenly spaced clusters. Okay. Good. But now we've got our scores. Let's go ahead and look at our plotting code and use those scores, right? So here, oh, I overrode scores. Good. So it does make sense to put it into. I hear this is a dictionary comprehension. That's probably what I should have done. But let me do my own code here. Okay, so I have scores, and I'm going to plot my scores, which I have from before. That's going to be here. And for this, what I'm going to do is I'm going to do range. I'm going to do 2 through 11. That's what I did before. Okay. Do I need to turn it into? Yeah, that's the thing. Do I need to turn it into a list? I think for both of these, I don't. Let's try it just, as it is. Okay. So good. I'm getting a very different plot. And I think it's a lot more interesting. It makes a lot more sense. So I don't know what is up with why am I getting such a different result here? Let me collapse this. Let's collapse actually all the plots. All right, so here I'm doing, okay, so the metric is L2. That's different. And I have here the labels. So let's look down here. When I do silhouette score, what's the default metric? Is Euclidean. But L2 and Euclidean is the same. Okay, just let's do a quick sanity check. All right, so here let's do metric equals L2. I'll be very surprised if we get something different. Okay. Metric. Oh, see, I forgot the quotes there. All right. Good. All right, yeah, so see, there's something else going on here. We're fitting the data set. We're fitting the same data set. We have the same N, but we're getting a very different plot. And this one here makes sense to me. Yeah. So the average, yeah, let's look at the code. You think it's all right, so here this average, we're simply passing in the score, and the score is here. We're getting from the X, the labels, and metric L2, and metric L2 is the same thing as Euclidean. So I can get rid of this and rerun this code, right? And I'll get the same results. Yeah, the results, they look the same to me. Let me just plot it again. Yeah, so it isn't that metric thing, that's for sure. Okay. And then the way I see it, it's silhouette score, X, and LBS. So it must be the data that's being passed in. So what's this? Where's this capital X coming from? Let's hear the values. You know what it is? I just realized. This X is coming from where we made blobs. Okay. The X is from earlier. This X here, it isn't our actual data set. It isn't the flowers data set. It isn't the iris data set. Okay. So that's something that's really interesting. All right. So we've got let's call this data set. Okay. And then here where we have X, we need to fit it to the data set. All right. And so that's unfortunately the difference. Yeah. Okay. So here, everything is correct. The best in terms of number of clusters is actually 2 for our iris data set. Let's do this again, but we're going to say plot silhouette diagnostics, and the data set that I'm going to pass in right here is going to be iris 40. Okay. So what does it say? Because I didn't run this. Yes, I hadn't run it, right? And then yeah, look at this, right? So 2 clusters, we're getting the best silhouette coefficient. Okay, and then you see how it's decreasing. This dotted line is moving continuously to the left. Maybe one thing that I need to do also is to do plt.x lim, and then here have it be from 0 to maybe 0.8. Okay, so that they're all, I need to make it, let's make it 1, because silhouette coefficient cannot be greater than 1, right? Yeah. And so all of these now, we've got the same kind of point of reference, yeah. And we can look at this red line, and it keeps going down, keeps decreasing as we add more clusters. Okay, so if we're going purely off of silhouette coefficient, the best is 2 clusters. Okay, and that kind of makes sense. Okay, we had our 1 cluster that really stood out, but the other 2 clusters were mixed together, right? And maybe we don't have much of a reason really to separate them. Okay, all right. So this is really good. We've got our silhouette coefficient. Okay. I think before we move on to the next part, we should take a small break. Okay. About 10 minutes. But before we take a break, I'm gonna talk a little bit more about what we just did. Okay. So this, unfortunately, what I had before, I'm gonna delete it now, was for that when we used from scikit-learn, we used make blobs. We had that synthetic data set that we just created. For our iris data set, really where it really only makes sense to have 2 clusters based off of silhouette coefficient. For the elbow method, I think that elbow was at 3, but again, it's subjective. With silhouette coefficient, okay, it's you get a value, and you can say, okay, well, the silhouette coefficient is highest for 2 clusters. Okay, right? Let's maybe look at it. What happens if we include 1, right? So here, this is going to be, what does it say? Value error. Number of labels 1 is, it doesn't make sense. Okay, so yeah, I think so too. Right? It doesn't make sense to have a single cluster. Okay. All right. Okay, good. anything else I want to, any other changes I want to do here? Oh, right. Let's maybe do a really quick plot. Okay, before we take the break, I know we were going to say take a break. Let's do iris. We're going to do iris data, right? So let's do the principal components again. Okay. So it's going to be this iris PCA. We're going to do the very first one. So that's index 0. We're going to do the second one, which is index 1. And then C is going to be iris targets. Okay. So let's take a look at that. This is here invalid. Okay, so that didn't work. Why didn't it work? Let's look at iris 2 PC. Oh, because I've got it's pandas data. And so what I have to do then is I have to use the ILO, and that's a pandas versus numpy. Okay. All right. So here I have, these are the actual labels on my principal component. Right. And if I look, iris, let's do iris target names. Okay. So the one that's 0 is Setosa. The one that's, let's add in the legend to plt.legend. So we don't know. So let's do label. I think there's a thing, right? There's a thing called labels. Do we have that? No, so is it label? Yeah, there we go. Okay, so yeah, I would have to fix this. But basically the plot that I have here, it's pretty good. These are the actual labels. So you see that there's one species that really stands off on its own, and another that's let me try one more thing with labels. So let's do range 3. And then now let's try to do legend. Yeah, labels. Let's do list. All right, so here haven't had too much success with labeling this well, but here are the actual species, right? And so you see that there are 2 species that are very close together, and I think that's versicolor and virginica are very close together, and then this one Setosa, it stands apart, so it's easy to distinguish that, right? Okay, good. And so Setosa, they have small petals, basically, right? These other 2, there's some, it's difficult to distinguish this. And if we look at this, okay, so the point that I'm trying to make here, if we look at this and then look at our silhouette coefficient, it really kind of does make sense to have 2 clusters. These species, versicolor and virginica, are hard to distinguish. It really is kind of one cluster here. Yeah, that we have. Let me see if I can shift the colors. Okay. So this being one cluster kind of makes sense if you look at it. Okay. Good. And I think the results will be the same if we use the PCA data. Right? That the best clustering results based off of silhouette coefficient is with 2 clusters. Okay. So that would be, we're basically saying versicolor and virginica are close enough that we just have them in the same cluster. And maybe for our purposes, that's good enough. Right. So really, we would be just mostly having a method that distinguishes setosa from the other 2. Okay. So how many clusters we want, it depends on the situation, right? But here, according to silhouette score, there really isn't much in the data that allows us to distinguish between versicolor and virginicolor, right? But if we look at this, we might say, well, actually, let's try it, because I can look and I can make kind of a decision boundary based off of these 2 principal components that will give me a good separation between the 2, right? So where would I put that decision boundary? I would draw it something like this, right? And then here, I'm only making, based off of that, this very, very curved line that I'm making, right? Is I would be making maybe 3 mistakes using this kind of a decision. Okay, 3 misclassifications. So I think certainly it's possible to do well, right? And then my clustering algorithm, based off of this, actually had 88% accuracy. Okay. Right. Remember when I did, I looked at accuracy score, right? So I could look at any of those other metrics, but accuracy is a good one to start with, right? So let's look at accuracy. So here I looked at accuracy. It's actually, let's round up to 89%. Okay. So not bad, right? Good. Okay, so now let's take a break because the next thing that we're going to talk about is a little bit of a departure. So I'm going to actually use, we're going to use a decision tree classifier. And so now we're going to include classification, dimensionality reduction, and clustering all in one. Okay, and that's going to be a little bit of a mental leap. So let's definitely take that break. Okay. Before we start this understanding cluster section. Oh, and then this is going to be so interesting when we get into the PCA. It'll be there are at least 2 mind-blowing moments that are coming. Okay, so stay tuned. All right, let's do a 10-minute timer. Okay, here's my 10-minute timer. I'll see everyone after the break. On my clock, that's going to be 12:48. Okay. All right. Thanks so much, everyone. See you after. Oh, and then yeah, definitely take time to complete the survey while we're on break. Okay. All right. Thanks so much, everyone. Oh no, I missed the question. Okay, so hold on. Stop. I missed the question. Oh yeah, so is your average silhouette score weighted by the number of points? Yeah, so that's it's an average. It's basically the silhouette scores of all of the samples divided by the number of samples. So the answer is yes. Okay. All right, we start. See everyone after the break. Okay, so welcome back, everyone. Hope you will enjoy the break. I think we needed it. We covered a lot. I mean, a lot of it was review, but digging deeper in things we talked about last time, talked about yesterday. Okay. All right. If you do have questions, definitely let me know. Right, but we're gonna move on. So today was what we did so far was huge into assessing, is our clustering working well? And also, what's the right number of clusters for k-means, right? We don't have to say how many clusters we want when we're using dbScan, but we have to set epsilon and then the min number of samples. But we can also use these metrics to say, okay, what do we want to do? Do we want to use k-means or do we want to use dbScan? We can also use silhouette coefficient to compare between those two different methods. Actually, that's such a good idea that I'm going to write it down, add it to our to-do list. Okay, so let's do compare dbScan, not scam, dbScan k-means, and let's maybe do another one. Let's do agglomerative clustering using maybe silhouette coefficient. Okay, so spelling some of these things is hard. Right? I have to think about it in French in order to remember how it's spelled. Okay, but I think I spelled all these things right. Okay, that's really interesting, but I want to leave that for later. Okay, because the things that I want to talk about now are really, really, really cool. Like I think basically like mind-blowing moments, I believe. Okay. So here there's this, it's kind of like a standalone thing. Here I've got my X and my Y. Here I'm pulling out the data and the target. That's going to be good. So I don't get confused about X and Y in the future, right? Because X and Y right now, that's that synthetic data that we had before when we used the make blobs function from scikit-learn. Okay, so here I run these imports. I create my data, and now I'm going to fit my data, and I'm going to go ahead and then do plot tree. Okay, so here's my decision tree classifier, right? And I have my target here, and so I can kind of look at this and kind of understand, right? So here I'm starting off with my decision tree where everything's at the root node. And a lot of the things that we talk about hierarchical clustering apply to decision trees. Okay, so we've got a root node. A root node has everything. Okay, and then we say, all right, if petal is smaller than 0.8 centimeters, right, is less than or equal to 0.8, then we say it's setosa. And actually, that's perfect. That's all we need. We have setosa perfectly classified. So no problem. So what is setosa? Setosa has small petals, and petal width is just, looks like that's the best. And we can perfectly classify setosa with nothing further, okay? But now between versicolor and virginica, those are those two clusters kind of that were mixed, right? That's where it's harder. You see, we have to do a whole lot more in order to figure out kind of what's going on, right? Okay, and we're going to do first split on petal width, okay, and then split on petal length, and then on petal width again, and then on petal length. And all this is great. We're eventually going to get it to be so that all of our leaves are pure. We only have one of each class. Okay, So here in this example, Setosa is the first, versicolor is the second, and Virginica is the last. Okay. All right. But this is a lot of decisions, and it's kind of hard to interpret. So what I might want to do is in my decision tree classifier, I'll want to do an argument and say here max depth, and let's do max depth of 3. Fit it again, plot it again, and now you see we only have basically a depth of 3, okay, and fewer decisions that we have to analyze and understand. Okay, so the cognitive burden for us is less. Okay, all right. So we got here Setosa, narrow petals. That's it. That's all we need. But then for versicolor, right, we can actually just split on petal width again, and we have most of versicolor figured out. Okay, so Setosa has smallest petals. Then versicolor has the narrowest petals. Then versicolor has the second narrowest petals, and Virginica has the widest petals. And from that, we're actually already doing not so bad. We only have 6 observations that are misclassified. So here I have 5 versicolor that are called Virginica, and here there's there's 5 Virginica that are called versicolor, and here there's 1 versicolor that's called Virginica. Okay, so 6 out of 150, and I'm making 2 decisions. I have 2 decisions in my decision tree, really using the same variable, right? Which is pretty good. And then if I do one more, now using petal length, right, I can do even better. Okay, so I can get it to the point where here I have 1 misclassification. Okay, so this is a Virginica that's called versicolor, and then here this is Virginica, right? And I have 2 versicolor that are called Virginica, and I know these names are not that intuitive, right? Okay, and it's hard to maybe relate to flowers. If these were something like, I don't know, fast food items or something like that, that would be best, or would be easier to relate to, right? Okay, but let's talk about, misclassifications. If you get down to here, how many misclassifications do I have? I have 1 misclassification here. I have 2 here. I have 1 here. And I have none here. Okay. So I have 4 misclassifications. 4 out of 150. So really not bad. But then the question is this really helping? Hey, I had 6 misclassifications before. Maybe this really isn't that useful. And so I may want to kind of set the max depth to be 2 and trim this further and say, okay, listen, just by doing petal width, I can classify these correctly most of the way, right? Okay. All right. So, so this is good. But what if instead of the target, I was using my clusters? Let's say I didn't have the clusters. Okay. So remember when I had my cluster labels? Yeah. And then I think all of this will work well. No, I need to do predictions. Okay. Remember I created that before. And so let's use the predictions. Okay. And try this again. Okay. So let's not include the feature names. Okay, because I don't actually have no, feature names are good, but let's not include the target names. Okay. All right. And so I have my 3 clusters, So 0, 1, and 2. How would I understand this? Okay. Well, you see, it's really set up very similarly. Petal width less than or equal to 0.8. Okay. For narrow petals, perfect classification, or all of cluster 1 or cluster 0 actually is split out by this decision tree perfectly just on this one split, this one decision, right? This one binary split. If this rule is true, then I say it's setosa, and I'm right 100% of the time in these things. Okay. So what am I doing here? What am I doing? Okay. I'm taking my predictions. Oh, and then you know what I might want to do? I might want to actually fit this to the two principal components, remember? Use it for PCA, right? Yeah. Maybe not, actually. Maybe not, because I want to understand, so this is about understanding. I'm going to want to use the original data. So my predictions come from PCA, but I want to understand. So I don't want to use principal components. I'm going to use the original data. I want, even though that also could be helpful to use the principal components to understand it in the context of the principal components, right? Let's maybe do both, okay? So first here, setosa is small petal width, but if I use principal components, right, and then here, all this is fine, but then I'd have to not have the feature names, right? So principal component 1, which is here indexed by 0. If it's less than 1.5, then that's setosa, or this cluster 0, and that's perfect, works perfect. Okay. Then still for principal component 1, if I have middle values, right? So between negative 1.5 and 1.6, right? Then I've got this here, and that gives me really, only, wow, okay, so look at that. Only 3 misclassifications. Okay. So for PCA, it's really good. Really good. Let's do a max depth of 2, because we really don't need it. Don't need more than that. And I know it's hard to think about this, but if you remember that PCA plot that we saw there was a cluster that was all the way to the left and it was orange, right? And that's what we're seeing here. So we've got our rule for this cluster here. If it's less than or equal to this principal component 1, which is x0 here, let me maybe do this. Feature names. I'm going to provide my own feature names here. So I'm going to say PC1, principal component 1, and then PC2. Okay. All right, brilliant. So now this should be easier to think about. Okay. So then maybe target names. Let's think about, is it target names? What's the class names? Okay. So I can provide my own names there. So let's call this like C0, cluster 0, cluster 1, and then cluster 2. Yeah. Good. All right, good. So this is really good. So here we have a mix. All the samples are mixed together. Then we say if principal component 1 is less than negative 1.5, we're going to say it's class 0. And how good are we in that? I mean, like, it's perfect. We don't need anything else. This is the one rule that defines class 0. Principal component 1 is less than or equal to negative 1.5. And if I go back to our PCA plot, you'll see that that's absolutely easy, right? So here, this is it. This purple cluster here, that's all setosa. You just draw a vertical line there, and we're perfect around negative 1.5. Okay. and it's a perfect classification. Yeah. Let's actually move this. And then for the scatter plot, there are quargs, so keyword arguments. And then I would probably I'd want to label this with a legend, but you know, maybe let's not go through the trouble of doing that right now. All right, let's take this plot because it's a good one and bring it down here. So when I'm looking at my decision tree, I can also look at this plot. All right, so this is the principal component plot. All right, and then here you see I'm doing principal component 1 is less than 1.5, and that's purple. So this one here, it's all purple. All 50 observations is purple. Yeah, good. And then down here, I have, you know, what's this cluster here? It's really, again, defined by principal component 1. If principal component 1 is less than 1.6, then I say it's cluster 1. If it's greater than 1.6, then it's cluster 2. And really, I only have 3 things that don't fit with these 2 rules. So these 2 rules, I'm able to do in principal components. I'm able to set this up, I think, really well, right? All right, let's change this a little bit. Instead of iris 4D, instead of iris 2PC to principal components, I'm going to do iris 4D. So let's do 4D. Yeah, and then rerun this. Okay. All right, so here, what do I have? I've got some kind of problem. This index out of range. I think what I need to do is I need to, oh, the feature names. Feature names, let's go, let's undo this, right? So we get our target names, we get our feature names, okay? And so now it's back the way that it was before, right? How many misclassifications am I getting? I'm getting 5 misclassifications overall, all right? Using the 4, so here, no, I need to have, let's do iris, we got to do iris target. And then we'll have it. Okay, so I'm basically just putting it back the way it was. All right. So here now with the 4 features, right? I have 2 splits and I have 6 misclassifications. Okay. All right. And then now let's do 2PC and see how well we do. Yeah. So I'm running this again. All right. And then, okay. Actually, you know what? With PCA, it seems like we're doing a little bit worse. We've got here 8 misclassifications for these 2, for max depth of 2 with this decision tree. Okay. So let's go back to how it was. I think the way that I had it was actually, you know, exactly right. Yeah. But the key thing that I'm saying here is if you don't have the labels, you can put in the predicted labels and then use the decision tree to understand the labels, right? So Setosa, which we had, maybe let's call it cluster 0, had the narrowest petals, then cluster 1, which is versicolor, had the second narrowest petals, and then Virginica had the widest petals. And just from that one feature, we can do a pretty good job of separating things out. Okay. All right. And so here, this is really the same thing, except for its agglomerative clustering. Okay. And again, we've got a decision tree, right? This is the dendrogram. We're looking at the dendrogram. And we get out, we can grow it until all the leaves are pure, right? So we have only one of each class, right? And then here, I think, yeah, I'm fitting it. The reason why maybe this doesn't work super well is because I would need to adjust the labels, right? So there's a little bit of a problem here with our data set, okay, where we need to kind of translate these cluster labels to be the same as our actual classes. Okay, so there's a step missing. And if I compare our cluster labels and then the actual target names or the actual target values, then I can see that disconnect. Okay, so let's look at the disconnect here. So here with these, I'm getting cluster labels from agglomerative clustering, and you see how easy it is to switch between algorithms. I just changed the name here. Okay, so I can switch between agglomerative clustering and k-means very easily. I don't even have to change this n clusters argument. It's the same. Okay. All right. Okay, good. And then, so one thing that I'm going to do is I'm going to just switch this out, actually, agglomerative clustering and k-means back when we were doing the silhouette coefficient, so we can compare the two, see which silhouette coefficients are better. Okay. Okay. And that could be a way that we would potentially be able to pick which clustering algorithm we think works best. Okay. All right. So another way we can do it is just doing it by doing it visually, right? So we had this plot k-means function, right? And then what we can do is we've got our x. We have our cluster labels. Our cluster labels are called cluster labels, right? We have our model, which is going to be dt, right? And then we have k, which is the number of clusters. Okay. So maybe let's do this. It's got to be, I think, just decision tree classifier. So plot k-means is not defined. Let's do 3. Yeah. So here. All right. So here I'm doing x. Okay. So here there are no cluster centers. That's fine. I think it doesn't matter, right? So here I can look at this, right? And then I'm going to try to switch it out to, I'm going to get that same error. I don't really care about it though. But I get out here these two plots, right? And I can compare agglomerative clustering and k-means, right? So here, let me do, this is going to be, let's do iris 2 principal components, and I'll make that same change here. Okay, so I'm still getting these errors, and I'd have to edit the function, and I don't want to do that. But if we look here, we can see, do they behave exactly the same way? On the principal component data, yeah, it doesn't matter whether I use agglomerative clustering or k-means, I get the same result. Like if you look at these plots, I get the same answer out, right? Oh, I guess the other thing that what I need to do, yep, okay. I need to make sure I'm using the same, I need to create the cluster labels. Okay. All right, so here let's do, let's move this down. Okay, so this is for, move this here. And this one here, I need to change to be decision tree class. Decision tree classifier, not decision tree classifier, sorry, k-means. Okay. Oh, and then here, k-means. So k-means. All right, this needs to be capitalized. Okay, good. Let's make this be a little bit easier. So here I just put in model, and here I put in. Okay, good. Are they the same? Yeah, they're still the same. Okay, so these two algorithms, they arrive at the same answer. So which one would I use? Well, that depends, right? Do I like k-means better? Or do I want to do hierarchical clustering, agglomerative clustering? Agglomerative clustering can be nice because I can get, I can still do this approach where I use a decision tree classifier to try to understand the meanings of the clusters, right? So that's an inference. What do the clusters mean, right? Cluster 0, what is that? In this case, what it is that cluster 0, I know because I have the answers is setosa, but if I didn't know it was setosa, I'd say, okay, those are the flowers with the narrowest petals. What is cluster 0? It's the narrow petal cluster, okay? And I can see that from the decision tree. It's a super powerful technique, okay? All right, and then I can use, here I'm using a plot to see what's the difference. I can see that cluster labels are the same. I think the silhouette coefficients then will be the same as well, right? For these, right? Because the data doesn't change. The Euclidean distance is both k-means and there's basically a distance metric that's used, right? Here's a machine learning flashcard for the principal component, and you can see here that I've got my x and y axes. I've got one feature on the x-axis, the other feature on the y-axis, okay? And then I'm drawing a line through them, right? And you can see exactly how, this is exactly how I explained it yesterday, right? This one line, this one dimension, the red one, replaces both of the dimensions on this plot, okay? So if I take this red line, right, I can see exactly where the points show up on that red line, okay? So I'm gonna do green because I think it stands out, and that's what I did last time, right? So here, this one is gonna be, that's really bad drawing. I have to try to make a vertical line. Okay, that's much better, okay? It's gonna be here, right? So this point is gonna be highest, has the highest value of principal component 1. Here, this point has the second highest value, okay? All right, over here, this point has the lowest value in principal component. So if principal component 1, if this was our flower example, this would be setosa. We draw some kind of line here, right? And we say, okay, If it's below, the actual values are kind of arbitrary, right? So if it's to the left of this line, we classify it Setosa. If it's somewhere in the middle, we're going to say that's versicolor. And if it's to the right, we say that's virginic. And we have our, one dimension that we can use for basically the clustering or the classification, whichever one we're doing. Okay. So the principal components, the transform data after we use principal component analysis to transform the data, we can pass in those transformed data to a clustering algorithm or to a classification algorithm. Okay. So very useful, very versatile technique. Okay, principal component analysis. That's the one type of dimensionality reduction that we'll learn about, but it's very useful. It's a super commonly used. Okay. Now, there's a little bit more to this PCA that I wanted to get into. Okay. So the principal components, right? How do we connect the principal components to the original features? Okay. And I will answer that question now, and it's going to involve us doing a little bit more PCA. Okay, so we've got here our PCA, principal component analysis. We're going to do two components. Okay, we do that because it's easy to plot it, right? And then we're going to, here we do fit, and then we do transform. I think we already know that we can do fit transform and it'll work just the same, right? But something that's useful here and that's new is we're going to create this data frame, okay, for principal components, right? We're going to get out the components. So this is PCA components 1, and we're going to do PCA components 2. And we're also going to get out the feature names from the original data set. Okay, so this is really cool. Okay, we see the components, okay, for how they are for the actual features. Okay, now we're going to look at this in a visualization, but let me first explain this, what we see here. Okay, so for principal component 1, remember this is the most important one. Always it's going to be the one that explains the most variance in the data. All right. It is largely synonymous with petal length. Okay. So what we see here, these components, let's see if we can get some documentation. It gives us a data frame. Let's do, I think we just have to look at PCA, and then we're going to go down to attributes. We see n components, and we see explain variance, we see components. Okay, so this is, what do they say here? It's the principal axes in feature space representing the directions of maximum variance in the data. Equivalently, the right singular vectors of the centered input data parallel to its eigenvectors. Okay, so I'm going to show this visualization. Basically, the way that we can think of this is how closely associated these things are. And they're going to range between -1 and 1. And so essentially what it is it's correlation. It's how well each of the features are correlated with each principal component. And you see petal length here, it's about an 85 or 86%, let's say, correlated with principal component. So they're largely the same. When petal length goes up, principal component 1 goes up, right? When petal length goes down, the first principal component goes down. They move together. That's the idea, okay? With sepal width, it's really not included in that first principal component, okay? It's close to 0. It doesn't have much of an impact on principal component, okay? All right, and then I would say sepal length and sepal width have, a moderate impact. Okay, so they're moderately associated with principal component. With principal component 2, what it is it's perpendicular to principal component 1. Okay, and so it's going to have a very different pattern, whereas sepal width had really almost no impact on principal component 1. It's got a big impact on principal component 2. Okay, petal length and petal width, not that much of an impact, right? It's mostly sepal length and sepal width, right? And so principal component 2, how would I describe that, right? It's basically the sepal size, what I was saying, right? So the length and the width of the sepals, that's principal component 2, okay? And I have a plot here. And finally, this is the plot that I wanted to show. All right, so it looks like it really was, I needed this code here. So this, I've got my principal components labeled beautifully. Principal component 1, 2. I have and I've got a legend. How did I even do that? Here I did legend. And I had to do label equals target name. I had to do a for loop for it. Oh, wow. Okay. And so Setosa is here all the way on the left. We know that. Low in principal component 1. Okay. Yeah. And then here for this quiver, the thing that I'm missing is to have a label for what these features are, right? And I think I need to maybe try to grab some code from that, okay? But principal components, I can look at the values and I can tell you, but that's not very clean. You have to take my word for it, right? Principal component 2 is based off of, first and foremost, this is going to be sepal width is this one here. Okay, so I'll label them by hand. All right. So let's put some text. All right. So this is going to be, let's just do abbreviations. So sepal width is this one. Then I've got sepal length is going to be this one. And then down here, I'm going to have petal length, right? And petal width. I'm going to draw little arrows to make sure it's clear which is which. Okay. All right. So here, sepal width is this one here. It has a small negative value for principal component 1. Okay. But it's got a large positive value for principal component 2. Okay. That's why it kind of, you see, it's pointing mostly straight up. Right? And then sepal length, it's got a fairly high value for principal component 1. Okay. But it has a much higher value for principal component 2. All right, so that's this one here. Okay, and then in summary, principal component 2, that's basically sepal size. Principal component 2 goes up when the sepal width and the length go up. It's collapsing those two together into one. That's principal component 2. What's principal component 1? Really, how I would describe it is its petal length and petal width combined with sepal length. Okay. So sepal length actually contributes a little bit more to principal component 1 than petal width. Okay. So maybe it's a little bit unfair for me to say that principal component 1 is petal size, because it also includes sepal length. And petal width and sepal length contribute fairly equal to this. Okay. All right, so this is a very useful way to try to understand. You can see how there are these features are being put together into the principal components, and they each contribute a certain amount, right? If a feature is not really connected with the principal component, it's going to have a small contribution. It's not going to have an impact, right? It's not going to be associated with the principal. Okay. All right, good. We have half an hour left. All right, and we're really getting to the point where I think you can do a lot of these things on your own, okay? So I'm going to continue to talk about things that I think are interesting. There's one more topic that I want to really hit. But what you can do is at the bottom of this notebook, you should be able to really work through all of the these exercises, right? And so it's going to be, all the steps are described, you know, step by step by step by step by step, right? This is the digits data set. I'm going to give you a little bit of time to work on this if you like. I'm going to jump back to metrics, and then I'm going to come back here to the digits data set, so we can together, I can show you how to get started with this. All right. So here, to load the data set, it's going to be, you do read CSV on this URL. Okay. Okay, and then there's going to be some pre-processing. That I think will be good if we work on that together. But once we have the data pre-processed, fitting the k-means, right? Calculating adjusted RAND score, or the adjusted RAND index, and then clustering, comparing clustering classification results. Those are all things that we've done. Okay. Before we go there, let's go back. I'm going to zoom out. So hold on to your eyeballs. I want to go back to where we had the silhouette coefficient. And I wanted to, I had my method here for collecting silhouette scores. Okay. And I'm gonna modify it, and I'm gonna say these are gonna be my let's say k-means silhouette scores, k-means scores, and I'm gonna do the same thing for agglomerative clustering. Okay, and I'm gonna compare, and I'm gonna see how it looks, right? So here I have k-means, but I'm not gonna do simply k-means. I'm going to have an argument here in my function that says model. Okay, so I've got let's have model be first. So model, the number of clusters, and then the data set. That's really how it flows here, which is nice. Okay, good. So I rerun this, and then I'm going to have my model. I'm going to say k-means. Remember, I have to have it be uppercase. K-means, so this is going to be my k-means scores, and then I'm going to have my let's do agglomerative clustering. So I'm going to call these AC and agglomerative clustering. Now I'm taking advantage of the fact that both of these algorithms, they're going to require me to say the number of clusters, and so the arguments are the same, really. Right, and I'm gonna stick to the two principal component data set. I think that's fine. It's in, you know, it worked really just as well as the original 4 features. So I think it's fine. Okay, so let's give this a try. Okay, so it's going to create a lot of plots and it's going to be working on this, right? It didn't take that long. But these plots are good. And I can look at them and I can say, all right, so here we've got 2 clusters. That actually looks like it's best for k-means. What about for agglomerative clustering? It also looks like it's the best, right? But now I can have a higher level view of all of this. Is I'm going to do my my plotting, right? Remember how I did my plotting? I actually don't know if I have that code anymore. So here, calc silhouette score. I have my scores already. I just need to do this plt.plot. So I'm going to copy this down. Get rid of the function. I already have my scores. You know what I should do? I should change these. This is going to be actually really good for us. I should change these list comprehensions to be dictionary comprehensions. Okay, so I'm changing the square brackets to be curly braces. And then I'm going to have here I colon for all of these. So I'm going to have the keys in the dictionary be the number of clusters, and then the values are going to be the scores. Okay, so let's go ahead and run that again. Okay, collapse the output, and then I'm going to do 2 plots. Oh, is this the one that I wanted to do? I think this is the one I wanted to work. Yep. Okay, good. So I'm going to do KM scores for both. And this is going to be number of, and then I'm going to put in a title. So the title here is going to be k-means. All right, so let's do that. So here I've got my k-means. All right, now let's do the same thing. Really same thing, except for I'm going to do agglomerative clustering. So it's going to be AC. AC. And then here I'm going to have to spell agglomerative again. Agglomerative clustering. Okay. And I can see that these plots look largely the same. Okay. So based off of what I can see here, let's maybe collapse the, let's just look at the plots. So we're just comparing the plots. The plots look, yeah, very similar, but they're not exactly the same. Okay. Right. So here the title, so this is actually the plot that I want to compare. Right. So you can see how here there's a little bit of a valley, whereas here there's, you know, the 2 plots are different, right? So sure. So this is k-means, and this is agglomerative clustering. Okay. For agglomerative clustering, I'm getting a silhouette coefficient that's a little bit higher, but it doesn't seem to make too much of a difference. Because I think it's a little bit higher. Maybe it's. Okay. Let's look at km scores dot values right here, and then these AC scores. Okay. So yeah, so the agglomerative clustering score for 2 clusters is a little bit higher. I don't know if it makes any sense to base a decision off of that. But for agglomerative clustering, something that we could do is plot, right? Create a plot that shows how our observations are being split up into clusters. Okay. For that, I don't have that here in this notebook, but in scikit-learn, if we go to agglomerative, no, that's a tough word. Yeah, agglomerative clustering. Let's do agglomerative clustering here at the bottom. So let me share this. I'm going to share it in Slack. Okay, so here, this is the link that's agglomerative clustering. And then at the bottom, it's going to be plot hierarchical clustering dendritic. Okay. All right, and if I just grab this code here, right, so let's do grab this code here. It's actually working with the iris data set, so that's pretty convenient. Okay, we can use that to plot results from our agglomerative cluster, right? And so how would I describe these? If you look at it, it's actually matches pretty much what we see, right? So over here, this is setosa, right? It stands alone, it's on its own. Then here we're gonna have versicolor and virginica that are tougher to distinguish. Okay. So I'll share this as well. I'm not gonna work on it because it really does do exactly what we're doing in the notebook. Yeah. All right. So it would be just running the code to reproduce this plot. Okay, good. We have 20 minutes left. All right, so let's spend a little time on exercises. I just want to get you started, and then you can continue on in these exercises on your own. So here, the components of this assignment, these are the pieces. Exercise 1, load the digits data set into a pandas data. Okay. Now, here it's not really explained exactly how to do this, but I'll give you a hint that, when we have PD imported, and so we import pandas as PD, you can see that here. We're going to have a read CSV method, and that read CSV method can work on files that are not local files. They're just, we get a URL, right? Here in this case, I see it's got a TES extension, which makes me think that maybe I need to reassess how to do this, right? But it seems like it works just fine, right? And so what's this TES extension? I really don't know. If I click on this link, so let's see, actually, I'm afraid it's gonna replace my notebook. But if I go to this link, right, it downloads this file. And it's not a file extension that's really known to me at all. But if I open this up in a text editor, I'd be able to say, okay, what does it look like? I think it's probably not worth us doing this. Yeah. Really, what we're doing is just reading the CSV, and that's fine. What I can see here is that what we want to do is we want to say header equals false, right? Because these aren't column names; these are values. So header equals false. What is it? It's not header. Header equals none. Okay, so it's just basically I did header equals none. Okay. Now I have a grid. Okay. So I have my 64 pixels in this data set. So it's Really what it is, it's an 8x8 matrix of integers that go between 0 and 16. So here I have all of these 64 pixels just as separate columns, right? Okay, so we say, someone's helping me out here with my understanding. Tests and TRA are extensions used for data sets that were pre-split into training and test sets when you upload them to UCI. Brilliant. Well, that's great. Yeah. That explanation is perfect, is wonderful. Thanks for sharing that. I wouldn't want to do that. You see, I got confused, right? But it seems like that's a convention that UCI follows. Right? And then we got the training set there. Oh, so we're working with a test set. Okay. Good to know, right? And so here we've got our data set, but we'll want to, we'll want to standardize it. All right, really, does it make sense to standardize it? Everything is on the same scale. We've got like 0 through 16. But let's go ahead and standardize it because these numbers, they're essentially meaningless to us. Right? These are pixel values. So how bright a pixel is, right? And we've got digits. Right, so the best explanation for this digits data set, it's actually in the Python data science handbook. Right, it has the best intro to this digits data set. Okay, so let's go to here, github.com. We get the full text for this. Right, so this is the link. So I'm going to open it. Yeah, good, boom. And then that's the link to the book, but then in chapter 5, which is the machine learning section, introducing scikit-learn, there's this great intro to this. Let's see, I think I already passed the start of it. Yeah, so let's just jump to digits. Okay, so we've got images of handwritten digits. Okay, so we do load digits. We could have also done that, right? Instead of reading it in from a URL, right? And here are the handwritten digits, right? So we see here, these are zeros. These are ones, some twos, threes, fours, five, sixes, sevens, eights, and nines. Okay, so that's what they look. And then each of these are 8x8, right? So we see 8 pixels in one direction, 8 pixels in the other direction. And the intensity of the pixels, at least in our data set, ranges from 0 through 16. Yeah. All right, so we've got 64 pixel values. So we've got here 64 columns. All right, here's a question. What if we had done load digits? Let's just try that and look at the data. So do we have data sets already imported? Yes, so let's do load digits. And then I'm gonna do .data. And it's an array. So to make it not a fair comparison, but an easy comparison is I'm going to turn it into a data frame. Okay, so this is another way that I could have done this, obtain these values. And you see the values are the same, right? Except here I've got, actually here it looks like I've got an extra column. Here you see this one, the 64th column. Those are the labels. So the labels here are included. Okay, so this is very, very important for us. So For scikit-learn, you want to split out the labels and the actual data, right? So here, let's do df. So really, it's a little bit more convenient to work with here low digits. But let me show you how I would split it, right? So here I've got my data frame, and then I do data frame dot iloc, and I'm going to say all the rows and then the last column. And this is my y. And my x is going to be going up to, but not including the last column. Okay, so this is a simple way I can separate out this last column. Okay, I'm using slicing in Python. Okay. And now when I look at my x should really be the same as what I see here, except, you know, here it's shown as floats, here it's shown as integers, right? But you can see it's the same. So 5, 13, 9, 5, 13, 9, 12, 13, 5, 12, 13, 5, right? And so imagine if we took an image and we just took all the pixels and we read them left to right. That's what we're seeing. Okay. All right, so we got our data set. So here I've got my x and my y. I set it up, I think, really nicely, and the code is good. Okay. Now let's scale it. Okay, so let's do from scikit-learn dot preprocessing import scale. Right? So we're just using the scale function. What does the scale function do? It subtracts the mean and then divides by the standard deviation. Okay. So then what we end up with is a mean that's very close to 0 or exactly 0. And then a standard deviation that's 1 or very close to 1. Why do I put very close to here? Is because there's a little bit of imprecision, right? So we may not get exactly a mean of 0. We actually very likely won't, right? It's just the way that Python works. Okay. All right, so now I've got scale, and I'm going to pass in my x here. Okay. And let's say scaled x. Okay. All right. The other way that I could have done this is do standard scalar. Why might I want to do standard scalar versus the scale function? It's because if I need to scale something again, the standard scalar class can remember the mean and the standard deviation that it used. And so I can easily kind of transform lots of data sets using the same mean, the same standard deviation. Okay. And it can remember, basically, right? So here, standard scalar, I don't really have to pass much in there, right? I'm going to just instantiate it as is. So I'm going to instantiate it as SS, standard scalar. I think it should have, right, transform. Actually, what I need to do is fit transform, pass in X, and there's my scaled X again. Should be the same thing, right? So let's see. So scaled X, that's what it looks like. And then we'll do scaled X 2, right? And so everywhere it's true. So I get the same, let's do this. Let's do all. Are all of these true? Maybe can we do NP all is true, okay? So for this, it doesn't matter what you use. But then after that, if I want to transform another data set, I might want to use standard scalar here, this class, because I got my class instance. And then if I want to transform something else, right? I have SS and I can do transform without fitting. That keeps the mean and the standard deviation the same. Okay. Good. But I've scaled my data set here. Okay. And then determine how many clusters, and then how many clusters using elbow method and silhouette coefficient. Okay. We have 7 minutes left. And I want to make sure that I'm answering any questions that you have. Okay. So before I go ahead and continue further with the exercises, I want to make sure that there aren't any questions. Okay. If you have a question, definitely let me know now, and I'll answer it in this time. Otherwise, what I'm going to do is I'm going to do this exercise here where I'm going to try to, from scratch, I'm going to collect inertias for k-means, and then I'm also going to do silhouette coefficients.
Yes, Martin, just a quick question, maybe to open the floor up too. Are you going to provide, I know the code exists in the machine learning book, but are you going to provide your notebook on GitHub for TA purposes?
Yeah, let's do, so this notebook that I have right now, probably the easiest way for me to share it is maybe not on GitHub, but rather for me to share that on Slack. Okay, so let me go ahead and share this now, this notebook that I have. So it's going to be here. I'm actually having trouble viewing. I have to move some of these windows. Zoom sometimes is a little bit obnoxious in the way that it blocks things, right? Okay. All right, but I got, I can see now. I'm going to share this notebook. So this notebook, it's a notebook as it currently is. Okay.
Yeah. Yeah.
So. Okay. And so I shared that. This is cluster.ipynd as it currently is. Okay. I think that's the easiest way. Now, keep in mind this notebook, I've done a lot of live coding in here. And so it's messier than what we started out with for sure. But there's a lot of additional interesting things, I think, in there. Okay.
Did you put it in which channel? Is it a general or the
module 3? Let me just put it in general too.
Yeah.
Okay. It's easy for me to do. Okay. Good. So it's there as in the general.
Okay.
Okay. Good. All right. So let's see. Any questions? Because I know there's relatively little time. There's 3 minutes left. I don't hear any questions. So what I'm going to do is I'm going to just quickly get these scores. Okay. So I'm going to start with the list comprehension. My list comprehension is going to use k-means to fit to the data. My data, remember, is X. So k-means, let's do n clusters equals I. And then we're going to fit to X. And then we're going to get the inertia underscore for I in range 2 to 11. And I'm speaking that those are just numbers I made up, right? And so these are gonna be my scores. Okay. Let's see, it's working. Oh, it worked. That's brilliant. That's so great. Oh, remember when I said dictionary comprehension is better for this, because I also want I want I as well. Okay. And then I'm going to do plt dot plot. And I'm going to have here scores dot keys on the y-axis. I have to call this is a method. And then I'm going to do the values. And I think that's it. There's my line, there's my elbow plot. Okay. So that was pretty quick and easy. Where is the inflection point here? Oof, it is tough to say. Maybe I need to do more. Let's go up to 50. Will we see a clear inflection point? Let's see in a second. Okay. Someone shared a screenshot. William, you shared the screenshot?
Yes, yes. So I think we may, I don't know, if you don't close your session, no one will be able to open it. So we can talk offline about that, but if anyone gets into that trouble because
oh, sure. I'm just running this locally, so I don't think it should affect anything other than just on my computer. But here's my elbow plot, right? In the last minute, I'm just going to say, where's the inflection point? You know, it's really tough to say. This is pretty smooth, right? I know that there are exactly 10 classes, really. So I'm naturally drawn. So the 10 classes are 0 through 9. And in this intro to data science, the Python data science handbook, you can see the 10 classes, 0 through 9. And this is a confusion matrix, right? So the right answer is 10, but you see this method is subjective. Is it 10? Is it 11? We don't actually know. We could do the same thing, except then plot silhouette coefficients, and then just say we're going to pick the highest. And that's a little bit more of an objective. Okay. Whether silhouette coefficient is a good way to pick between different model types, I say I would be a little bit worried about that, to be honest. But at least, you know, same model type, different number of clusters, silhouette coefficient is. Good. All right, so with that, we're at time, actually 1 minute over. I think there are no further questions because I paused for questions. So I'm just going to say thank you so much, everyone. This was a blast. I very much enjoyed teaching this. We covered a lot of really advanced concepts, and I tried to connect what we discussed today with what you learned previously. You learned pandas, you learned classification, and I think I included a lot of that here in this module. And I wish you best of luck in your learning journeys, and then I hope you enjoy the remaining modules in this course.
Yeah, so Martin, thank you so much for your support of this initiatives, and thank you for an excellent presentation. And then, as usual, I hope that next time when you are doing it, you will be available to support us. And thank you all for coming. Next week we'll continue, but next week is going to be a little different. It's not going to be an instructional section like this. Next week we'll what I call for the seminar presentations. So there will be a presentation on ethical data science. There will be a presentation on data science and social justice. There will be one on data science and environmental health / environmental justice. And then there will also be a presentation on elements and use of EHR discovery. So it will be interesting. I think each presentation is about between an hour and 75 minutes, depending on what the presenter wants to do. So you are all welcome, and then you can also invite your friends and colleagues to join. It will be an interesting 2-day section, so you will at least be a little free from all the technical details of data science. Any questions for me or any questions? And then also again, please take a moment to complete the survey. Any suggestions that you may have for next program, you are free to do so. And then again, your feedback is very important to us. Thank you.
Yeah, and John, I think we may also add that there will be TA session as usual.
Yes, yes, yeah. So go ahead, William, with that.
Yes, yeah. So there will be TA session on Saturday, and it will be posted. I mean, we're going to use the same Zoom link, but if you can't find it, just go to the general channel or the TA channel and the TA channel. We'll post the links on both places. It's 5 to 7 Eastern, 5 p.m. to 7 Washington, D.C. time. So see you all there. Thanks. Okay, so back to you, John.
All right, so we are all set. Enjoy the rest of the day and then the rest of the weekend. Thank you. And Martin, thank you so much again. All right, take care. Bye, everyone.
Okay, take care.